Warm greetings, everyone. So we'll see the continuation of the electric potential energy. So in addition to that, I want to confirm with you. Actually, the potential energy of a system of charges we saw, right? So the potential energy is mainly, first you saw the system of charges, okay? In this system of charges, it means it is the energy stored due to mutual interactions between charges in the system. Okay, the charges interact with each other. See, for example, here at a B and A. So this point we can say charge 1 and charge 2, it is moving from place A from A to B. Okay, so the work done in moving charge 2, second charge from A to B. Here you can see the mutual interaction between the energy stored is due to the mutual interaction, okay, between the charges. Energy is required to assemble the system from infinity. That's what you have seen the formula for two charges, K into Q1, Q2 by R, right? So that is the potential energy. It depends on the relative positions of charges. See here, relative positions of charges, okay, mainly. And then we can say it is the internal property of the system. It depends on charges interact with each other, negative, negative or positive, positive. So we saw if both the charges, so I can able to say here, first negative, negative or positive, positive here. So that is Q1, Q2 is greater than 0. Product is greater than 0. And if these two are, and then these two forces are, repulsive force, everything we saw. Okay. So here also the same. So I can able to understand, I can make you understand all these steps. What is the major difference between potential energy in a uh, due to the system of charges and then potential energy in an external field. Okay. Do listen carefully. And then it can be positive or negative, everything we saw, right? For many charges, which is attract, repel, everything we saw. See, for example, I will give you this example. The sum of all pair interactions are for many charges we saw, right? Sum of all pair interactions means Q1, Q2 and Q2, Q3, like that, everything we saw. Okay. So you can watch that video, the previous video, which I have uploaded for the clear understanding from the NCERT book. Okay. This is, I have explained you the major difference between, okay, the potential energy due to the system of charges, the potential energy in an external field. First, it is due to the system of charges. As I told you, the interaction takes place with each other. Okay. So energy is required to assemble the system from infinity. That is the point. Okay. Next, here, some example problem. What is the electric potential energy of the group of charges in the figure? That is the question, for example. Okay. Electric potential energy of the group of charges in the figure, this figure. Okay. So what is this given in this picture? What is the electric potential energy? Here, you can say. Okay. What is given here? Negative charges here, both are negative. Here, both are positive. Then positive, negative. You know, how can we calculate this? The same formula, right? This is the formula. So it might be asked like, how much energy does it take to create this charge configuration? That will also be asked. So you have to consider different charges, different, three sides, on the three sides, and then you should sum. Okay, take a sum of all these things based on the derivation I taught you from the NCERT book. Okay, take it as a assignment from this. Then I'll explain you. Then we'll see what is potential energy due to a charge in an external electric field. Okay. So in an external electric field, if you say the charges interact with the field created by the other sources. So the charges interact with the field. If you see here, at a finite distance from the charge 1. Okay, you can see here right now. So a finite distance from the charge 1, here it is at infinity. A point is infinity, we can take. It is a finite distance from the charge 1. Okay, this is the major difference actually. The charge 1 is it is having electric field here. So what is electric potential energy? We can so call this name as electric potential energy. So the energy of a charge due to its position, okay, in an external electric field. That means the charges interact with the field created by the other sources. Okay, so work done in moving charge 2 from A to B. So that is electric potential energy. Next, I can say, for example, see, for example, here, already we saw all the derivations from your book. Right now, I'm explaining, okay, what is the major difference between this? Okay, not a difference. How can we able to understand the potential energy due to a system of charges, potential energy in an external field? Okay, so not due to its own system interactions here. The interactions is with the field created by the other sources, not with its own system interactions. Okay, so here the formula is U is equal to QV, we can take. Okay, you know the positive charge Q naught moves opposite E. E is the field given here. Q naught is moving oppositely. So field does negative work on charge. So U increases. Okay, potential energy difference, energy is increasing. Work done is negative. Okay, electric field, you can see the electric field. Okay, Q naught is moving opposite to the electric field. Okay, so everything it is given clearly in this picture. So you can able to see this. See high potential to low potential, we can say. So this is the test charge. So right now, high potential to low potential means the charges are moving from high potential to low potential. So you know the formula here is U is equal to Q into V. We can take. Okay. And then it depends upon the position in the field. Very important. Field is already present. Okay. But it depends on the position in the field. Okay. So I can say first we saw the potential energy to the system of charges. It is self-interaction. Here, the potential energy in an external field is outside. The interactions are outside with the field. Okay, say like this. See here, you can easily understand how the positive charge and negative charge, how the electric field will be, right? So it is major application. So the major application you are going to see this. It is used in the problems like capacitors, electric fields, some circuits, everything we are going to see. This is the parallel plate capacitor. So we are going to see that. Then you can able to understand and apply this principle over there. So electrical potential and the voltage. This also you are going to study in your next lesson. Okay. So this also I have explained you. KQ by R means there's a potential difference, right? The work done in moving charges from one place to infinity to one point is potential. From one point to another point is potential difference. Okay. See here, this is clearly mentioned what we have seen in the last class. See, this is the equipotential line. I taught you already. Okay, and then this black color is potential, electric field line around the, radially around the positive charge. And now the charges are displaced from A point to B point. So this is the source charge. And then unit positive charge from A to B, it is moving under the influence of this particular electric field. Can you able to understand this? You are going to study here the Q naught is moving from A to B it is like a path dependent. Like this also it moves, like this also it moves, like this also it moves in the electrostatic potential. Okay, so if you want to measure the potential energy from this to this, the work done has to be calculated. So in the field, so it is interacting with the field. Okay, so it is very important you have to understand. We are going to study about this also. So what is the potential difference? Potential difference is E dot ds. I told you no work done. Work done is the potential difference. Work done can be F dot ds, or F can be written as E into Q, where unit positive charge Q is equal to 1. So E dot ds. It forms angle theta, E and ds. So it forms, okay, two component, E cos theta and E sin theta. So both can form a component. Either ds form a component, or if you take d, because ds also an element, vector element. E also forms a component. Okay, so if you take E ds cos theta, that is also possible. Okay, so E cos theta into ds. It is the main explanation for the potential difference. And then you know about the equipotential line. So then we'll move on to the next. I will explain you right now. We'll see the next question. So we'll see the next. Students, now you can able to understand the difference very easily. Now we'll move on to the next. Next talk about capacitors, okay, insulators, everything. So it is the theoretical part. What are the electrostatics of conductors? This and all I've explained you fully, okay? So I have explained you as a story, right? Copper story. You know the copper story, right? All about this, you can go through it. Okay, so inside a conductor, electrostatic field is 0. Everything is given here. You can go through it. This is a very easy topic only, not a very big topic, or I can say. Okay, now we'll see all the electrostatics of a conductors. Okay, so what is the electrostatics of a conductor? We'll see. First of all, you must learn about what is a conductor. Okay, so a conductor is a material like metals. Yeah. So we'll see what is a conductor. A conductor is a material or like metals. Okay. And then that has free electrons which can move easily inside it. So always I taught you about what are the electrostatics based on the copper wire. Okay, so the copper story you learned. All these, so 1 centimeter of copper wire, and I've explained you all the stuffs, right? And then you know about the conductor and how the system of charges, surface charges, right? Okay, the charge density at the surface, everything you saw, right? So here, how the conductor and dielectric will be. Dielectric or the insulators. Okay. Here in the conductor, this will be E naught. Okay. E naught, and E naught is the direction. You can see the direction. Okay. Here a normal, right? So this is also direction you can see. Okay. So these two directional thing, or actually here it is equal to 0. That means both are same. for a conductor. Okay. So here for a conductor, it is not equal to 0. So then that is the dielectric. Okay. So this is the major difference between the dielectric and we are now going to see all these stuffs. And then here conduction of electrons also, everything I've explained you. It is talk about the current. If it achieves the drift velocity, it moves into the free electrons. That and all that shows the free electrons are responsible for the current. Okay. Now, next we are going to see in your book it is given as electric field inside a conductor is 0. What is electric field inside a conductor? Now I'm going to show you. See here, this is the types of electrostatic charges, right? I taught you already. So we exaggerate this. Okay, if you cut the cross section of a wire, then you may found n number of positive and negative charges. Positive charge is nothing but it is the positive ion, copper plus ion, right? Okay, then we will see. Then we'll move on to so electric field inside a conductor is 0. Suppose when equilibrium is reached, what is the equilibrium? I told you E external, E internal. That is here positive surface charge density. Here it is negative surface charge density. If both are same, okay, then that is E external is equal to E internal. That means if these two are 0, that the plus sigma minus sigma equal to 0. Then we can say it is the conductor, right? So there are no charges inside this particular field. So that is what given here. Inside this conductor, there are no charges. Okay, the charges inside the conductor is 0. Okay, so when the equilibrium is reached, electric field inside is 0. Since the charge is 0, no. Rho is nothing, it is the letter given for volumetric, okay, charge density. So volumetric charge density is 0 inside the conductor. You can able to understand. Sigma also 0. If you draw a cavity, then sigma also 0. Okay, so sigma means it is a surface charge density. So it is 0. Got it? So sigma is 0. Rho is also 0. Then you can say electric field is 0 inside the conductor. Okay, if you take a conductor, then electric field is 0. So only at the surfaces electric field present E1 and E2. If it is a conductor, definitely E1 is external field, and external means that if it is positive, the field is external. Okay, if it is positive, how the field is external, right? If the field is negative, the field is internal. See the arrow mark? Okay, positive charge and the negative charge. So at the surface only the charges are present. Inside the conductor, there is no charge. So volumetric charge density or surface charge density, everything is 0. Okay, so that electric field is 0 field. Okay, I hope you can able to understand this. Okay, so this and all talk about all these structure. Okay, positive to negative. Everything you have already studied in the Gaussian surface. E dot A is the flux, right? So if field existed, electrons move, okay, and then not equilibrium. Like if it is there, it means internal E external. If you are adding these two, if the resultant is there, not equal to 0, definitely it is not in an equilibrium. So basically, the charges rearrange until internal field cancels. Okay, until internal field is 0, until then the charge rearranges. Got it? Then we'll move on to the next. What is the next given in your book? Then I taught you the electric field is perpendicular to the surface of the conductor, right? So how it is perpendicular to the surface of the conductor? This is how. If it is a conductor, electric field is zero inside and it is perpendicular to the surface, right? So see, we can construct a Gaussian surface like this. So it is a conductor, okay? And then the Gaussian surface can be constructed by means of this, right? So partly it is in the free space, okay? You can construct a Gaussian surface, okay? Then see from the center of the conductor, field lines are away. So you know all these stuffs. If there are negative charges, then the field lines are going inside. And then this I taught you already. Always the electric field is perpendicular to the surface we have constructed. So if there is equipotential surface, there also the electric field is perpendicular, normal. Okay, normal to the surface. See how the electric field is normal to the surface. If it is perpendicular, you have to take from this, if you consider the electric field like, okay, if it forms an angular, the electric field is like this along the surface, then you have to construct a component. One is perpendicular component, another one is cos theta component. Okay, or parallel component, we can say. So parallel component is Q into E. This perpendicular component is the matter. Okay, so this is what we can say electric field is always perpendicular to the surface. Okay, then here also it is clearly demonstrated, right? How the charges are producing field. Okay, you know this kind, right? In a quadrant they have given. Okay, they have taken like a quadrant where the electric field is present. Okay, so this is not as much important. You have to understand how the charges are, how the electric field is perpendicular to the surface. Okay, Gaussian. So we saw excess charge always moves to the outer surface. Okay, inside the conductor, no net charge. So this we saw. Electric field is perpendicular to surface means no tangential component of electric field. That is the meaning. Okay. Otherwise, charges would move along the surface. So field is always normal to the surface. Okay. So this thing you have to understand. And then if the potential is constant, all the equipotential body, entire conductor has the same potential everywhere. And then you know the energy, the electric field is perpendicular to the surface. Okay. So surface means at the surface, if you take the potential difference for the equipotential surface, I'm saying if you take the potential difference is zero. Since entire conductor has same potential everywhere, so at the surface and inside there is no potential difference. Okay, is it clear for you? That's why current doesn't flow inside in electrostatics. In electrostatics, we didn't see any current here. Okay, can you able to understand this? So right now we are going to see electrostatic shielding is given here, group. What is electrostatic shielding? Electric field near conductors, right? If it is hollow, excess charges moves to outer surface, we know. Okay, what is the shielding? Okay, so a closed metal container will have no charge on the inside surface, we saw. Closed, right? But if it is a shallow, hollow conductor, definitely excess charges moves to outer surface. Okay. So what is the shielding? We can say a conductor blocks external electric fields. Okay. So inside region becomes field free. That is, we can say always it is the Faraday cage, we can say. Okay. Cars during lightning, how it is. So I will show you this. It is lightning, okay? The charges dissipates in the ground. It won't affect the car inside. So it is like a Faraday cage. Charges are not getting, the potential difference is not created inside the car. All the charges are dissipated in the ground. It is lost in the ground. Dissipated means lost in the ground. See here. So field pushes electron towards left side. So net positive charge remains on the right side. Okay. So this is what electric field is zero inside. Okay, field perpendicular to conductor surface, everything it is given. Okay, so it's a very great example for electrostatic shielding. Okay, and so we can able to see all these stuffs. Okay, it is electrostatic shielding. Okay, so this is a famous example. You can take it. Okay, Faraday cage or cars during lightning, like that we can say. Okay, from this you have to understand. Inside the conductor, electric field is zero. Okay, keep in your mind, all of you, my dear students. Inside the conductor, electric field is zero. Okay, so at the surface, charge accumulates. Sharp edges, if you say at the sharp edges, more charge density you can able to see. That is high sigma at the sharp edges. If it is hollow cylinder, inside cavity, we saw, right? E is zero. If no charge inside, that is E is zero. Hollow conductor, right? So, you can keep in your mind, I will tell you right now, zero, keep in your mind, zero field inside. Okay? Charge outside. Then same potential throughout. Okay? So these 3 points you have to take in your mind. So this is one line memory trick like that. You can take zero field inside, charge outside, same potential throughout. Okay. So students listen, conductor is very smart. It pushes all charge outside and keeps it inside completely peaceful. So E is equal to zero. Okay. Okay. So we'll move on to the next topic right now. We'll see. So this is the next topic.